That's good. Hello, everyone. Thanks for being here today. It's my great pleasure to introduce Cody Ratterman, my second PhD student. Before I get down to the topic, but I want to say that Cody is a student that who has driven me to think, and he really inspired me to some extent to the topic that we're working on. So Cody has been working on understanding a very important driver for drought, that's precipitation. He has been studying understanding precipitation phase, total amount, but also the measurements and using machine learning. So Cody is going to walk you guys through all the process, all the research he has done over the past 5 years or so. Again, thanks for being here, and also thanks to the committee members who has given Cody a lot of advice over the years. Without further ado, I will turn the time to Cody.
Thank you. Yes. Thank you, everyone, for joining me today. This whole defense has the overall title of Understanding and Predicting Precipitation Characteristics in the U.S. through Machine Learning, Numerical Modeling, and Measurements. Thank you all for coming here to be able to help me share my story. This is what I've been working on over the last 4.5 years during my time at USU. I came to Utah State University starting in 2022, initially as a master's student, and then I signed up a couple years later to transition to becoming a PhD student. I started my internship with Apogee Instruments 3 years ago this summer in 2023. And I've enjoyed working on helping develop some of the sensors there as well. I've gotten to travel to conferences across the country from San Francisco to New Orleans and Washington, D.C., being able to share my story and my research with lots of people and learning from some really great hardworking scientists along the way. In the 2024-2025 school year, I was awarded the Doctoral Student Researcher of the Year for the College of Agriculture and Applied Sciences. When I'm not at school researching, I often really enjoy getting out rock climbing. It's a really great practice in taking really big, intimidating goals and breaking them down into smaller, more manageable parts. And when we do this, we often have to pay a lot of attention to the environment around us. There's things like water levels that change in the spring and cause seepage. In the wintertime, snow and ice conditions matter a lot. And paying really close attention to small changes in temperature, relative humidity, and even the wind can make the difference between being able to hang on to these really small holds or not being able to have any chance at all. However, my favorite is being able to go up to the high elevation alpine regions. These big mountains are really intimidating and humbling, but they're also inspiring. They've been around a whole lot longer than we have been, but yet they're also slowly changing. The glaciers at the bases are getting smaller and smaller each summer. The summer rock season is getting longer with the warmer summer temperatures, and the afternoon scattered thunderstorms are becoming less frequent, but often more and more intense every year. When I'm not out climbing, I often enjoy shooting archery. It's a really great practice to be able to combine the physical setup of your bow, your technical shot process, and your mindset. Whenever you try to get better, you end up changing one of these. However, it's all an interconnected system, so you make small changes to one, and it ends up affecting all the others as well. So it's a constant work trying to find a balance in between all three. And when they are in a balance, things feel great. It's almost perfect. But then there's always that one arrow. And it always reminds you there's always more to learn and keep working on. It's a quest for perfection, which truly never ends. I was grateful to be able to work with the Climate Adaptation Science program here at USU for several years as I was a student. This is a collaboration between students and professors and local government workers in order to collaborate on a project together. Our project focused on the Great Salt Lake wetlands. What we learned is that as the Great Salt Lake is shrinking due to the lack of precipitation combined with more and more people taking water that would otherwise go to the Salt Lake, means that the water levels are shrinking and the wetlands are moving inward with it. This is creating threats to the local birds and wildlife in these areas. And so we wanted to understand how much they're changing, what people are doing in order to help conserve it. And so the Great Salt Lake shrinking is one of many signs of the water usage and drought problems that we have in the Western US. The plot here shows the average daily domestic water usage per person in the US. And you can see that Utah is in this dark blue color, which is the highest water usage level. And on top of that, the numbers inside of each state show the average population growth from 2000 to 2020. So in short, Utah is one of the highest water using states per person. And on top of that, it's also growing at one of the fastest rates. And on top of all this, we've been experiencing a lot of droughts recently, which is limiting our water usage. So we're having less water, but needing to use more of it. And so this creates a lot of water budgeting problems, which we need to plan for through precipitation forecasting. And recently, just last week, the government even announced a state of emergency for Utah's intensifying droughts, signifying how big of a problem this really is. So water usage should be pretty simple. It covers the majority of Earth's surface. However, 97% of it is ocean water, and the other remaining 3% is fresh water. So we don't have that much water to actually work with, but it gets even more complicated because 2.5% of all that water is not actually usable fresh water to us. It's locked, frozen in glaciers and ice caps. It's evaporated in the clouds in the atmosphere. It's dangerous, being polluted, making it unusable for us, or it's buried deep underground in the groundwater. This leaves only 0.5% of all water on the Earth as usable for us in the form of fresh water. And this usable water ends up in our rivers, lakes, reservoirs, in the form of rain and snow, and in snowpack and soil moisture on the ground. And it's all being constantly redistributed within the water cycle. So when we forecast precipitation, we're trying to forecast where and when this usable water will be present. So what is precipitation? Precipitation is simply defined as hydrometeors. That's hydro as in water, and meteors as in falling from the sky to the ground due to gravity. And it comes in many forms. It can come in the form of rain, hail, sleet, freezing rain, graupel, or even snow, depending on a lot of environmental variables and the temperature profiles. And seasonal precipitation forecasting is extremely challenging. This is because the weather is chaotic, and so small changes in initial conditions will lead to much more dramatic outcomes down the line. And so what we do, instead of trying to predict the exact amounts, we create forecasts that will say whether we're going to be around average, below average, or above average. And so this is an example for a forecast of the December 2022 to February 2023 winter, which, if any of you that live here remember, we received record snow in Utah, and it was forecasted to be right around average. So there's obviously a lot of room for improvement here. This dissertation has the introduction chapter, which we've just finished, along with 5 research chapters, which we'll go through one by one, and then ending with an overall conclusion. So the first chapter is improving the CFSV2 seasonal precipitation forecast across the US by combining weather regimes and Gaussian mixture models. So what are weather regimes? Weather regimes are large-scale circulation patterns based off of 500 hectopascal geopotential height anomaly. These geopotential height differences indicate the locations of high and low pressure systems. And from these high and low pressure systems, they can indicate a lot to us about the general weather patterns in the area. Days with similar weather regimes will end up exhibiting similar temperature and precipitation patterns. Areas under a high pressure ridgeline tend to have higher temperatures and be warmer and drier. The areas underneath low pressure systems tend to be cooler, and the low pressure allows for air to rise, forming more precipitation. And Dr. Zhang did a study just a few months before I joined his team, in which found that the Western US has been experiencing fewer trough patterns, which is contributing to these increasing droughts. So if we can use these weather regimes to help us understand weather patterns on a longer multi-year climate scale, is it possible to be able to use these for a monthly scale, as in a seasonal prediction a few months out? That's the question we try to answer in this chapter. When we create weather regimes, historically, most people have used the k-means method. This is a deterministic method. So we have groups of clusters of different weather regimes, and whenever we have a new point, it's assigned to the nearest cluster, and then we adjust the cluster to include the new point. This means that when we use k-means, each day of the forecast would have an individual weather regime. However, things aren't always specifically one of these categories. So in order to include these in-between days, we use Gaussian mixture models, which is a probabilistic model. Rather than being a singular point and a cluster, it's a series of distributions, and these distributions overlap. So each day is assigned weights for each weather regime, and all those weights add up to 1, as you can see in the bottom right-hand corner. So the procedure for building the weather regime Gaussian mixture model, or WRGMM, as we like to call it, is we train WRGMM and create weather regime probabilities within the climate forecast reanalysis, 500 hectopascal anomaly from 1981 to 2010. We then create 60 different precipitation profiles, that's one for each month and each of the 5 weather regimes, using CPC precipitation observations during the training period. Only days categorized as being larger than 90% of a single weather regime were used in order to throw out these in-between days. We then use the trained mixture model to create weather regime fractions for the CFSV2 forecast. And so we take the 500 hectopascal geopotential height anomaly data on the first of each month, forecasted for the next 4 months, from April of 2011 through April of 2022. We then convert the daily forecasts in weather regimes to monthly averages of weather regime weights. And from this, we can use the weather regime fractions that we have in step 4 and connect them to the past precipitation maps made from step 2 with all those precipitation profile maps. And we end up having a final forecast that looks something like this. These are 2 example months from March 2022. And in the upper left-hand corner, you can see the actual precipitation observations. In the middle is the original CFSV2 forecast. And on the bottom is our weather regime Gaussian mixture model. And on the right-hand side, you can see the bias. And you can tell that all these colors are more faded, indicating that the bias is smaller in WRGMM than CFSV2. And before we go too much further into the analysis, we want to look at how accurate CFSV2 is actually at predicting the weather regimes themselves. And so we plot the average weather regime weights in CFSV2 on the X, and in the reanalysis data from actual historical periods on the Y. And we find that they have a pretty good correlation, as shown by the general line from the bottom left to the upper right. And so when we look at the annual average precipitation bias, we can confirm that WRGMM has significantly less bias, as shown on all of the plots along the bottom. And we also look at the correlation. Anywhere in green indicates a positive correlation. The red, or the little black dots, indicate areas where there's a significant correlation. And the bottom shows the difference between the correlation in WRGMM and CFSV2. So everywhere in red along the bottom shows times and areas in which WRGMM has a higher correlation than the original CFSV2 forecast. And this work has been continued with a NOAA grant by one of Dr. Zhang's postdocs, Dr. Jihoon Ryu, and he's been working to improve the WRGMM method, and he's applying it to other models besides CFSV2 to get the most potential out of this method. So in conclusion, weather regimes are categorized weather patterns based off of 500 hectopascal geopotential height anomaly. These exhibit similar temperature and precipitation patterns. Gaussian mixture models allow mixtures of categories with daily 500 hectopascal geopotential height, represented as fractions of multiple weather regimes rather than individual categories. These matching daily weather regimes and Gaussian mixture model weights in the CFSV2 forecast improves the forecast skill, as shown by having less bias and higher correlation in the 1 to 4 month seasonal forecasts. This hybrid statistical dynamical approach improves precipitation forecast skill, and as a side effect, also increases our resolution because the observations that we're using have more grid points than the original CFSV2 forecast did. And so it's great that we can have a more accurate precipitation forecast, but as anyone that lives in the Utah area generally knows, most of our precipitation comes in the form of snow. So what we really need is a snowpack forecast for the Utah area. And this brings us to the next chapter, in which we are improving CFSV2 snow water equivalent forecasts in the Colorado River Basin with generalized analog regression downscaling. So whenever snow falls, it initially falls in a given depth. When that snow depth melts, it becomes a much smaller amount of water. We call this snow water equivalent, or SWE for short. When this happens in the real world, it actually translates into being runoff. This means that the snowpack in the high mountains melts and ends up going into our creeks and then rivers and then lakes and eventually reservoirs. So all that snow that's in the mountains in the wintertime generally ends up in our reservoirs at the end of the spring. This ratio of how much the original snow depth is to the snow water equivalent is generally, as a rule of thumb, we use 10 millimeters of snow to about 1 millimeter of water. However, this can vary anywhere from 2 to 3 millimeters of snow to 1 millimeter of water in really ripe, dense slush, or it can be as high as 20 millimeters or even 30 millimeters to 1 millimeter of water when we look at that really light powder that we love to ski on. We measure snow water equivalent in kilograms per meter squared. We basically draw out a square kilometer on the ground and weigh how much snow is on top of it. And when all that melts, it conveniently leads to when 1 kilogram per meter squared of snow melts, it becomes 1 millimeter liquid depth because the metric system was conveniently based on water. And snow water equivalent changes a lot from year to year. This is a plot of the first winter I moved to Utah. I came here in January. Everyone was complaining about the droughts, and I was like, guys, there's snow on the ground in April. This is more snow than I'd ever seen. And then the next year we get this, literally twice as much snow water equivalent as the previous year. And I was left wondering, what is an average snow year? Which has only made me even more confused by this year being the record low. So yes, there's a lot to learn from this. And on top of that, neither the record high or the record low was accurately forecasted until we were already halfway through the season. And so CFSV2 has a problem when it comes to snowpack. It's mainly its resolution. And so as you can see, CFSV2 does in fact have snow. It's just there's so little that it doesn't show up on the color bar when compared to the actual observations. And this is because, if you notice, most of the snow occurs in the mountains, and CFSV2 has a 1 by 1 degree latitude longitude resolution, which flattens out all our mountains. So if we don't have mountains, we don't have snow. So this looks something like this. The pixelated Mario is representative of the CFSV2 forecast. And what we want is more similar to our actual observations. The NSIDC is the National Snow and Ice Data Center, and it has a 4-kilometer resolution. There are 590 times as many grid points in the NSIDC data set than the original CFSV2 forecast. And so how do we get from the CFSV2 model to the NSIDC resolution? We use a technique called statistical downscaling to go from the resolution in A to the resolution in B. So let's go. So what statistical downscaling is it takes an initial model, which has a low resolution, and it puts it into a function, which then converts it into match the high resolution of the observations. The way we do this is we compare the future forecasts with historical forecasts that have already happened. These we call hindcasts. They were typically not correct. But what we can do is if we look at an upcoming forecast that uses the same dynamics as it has before, and we assume that it's going to be incorrect, if we go back in time and find similar hindcasts to what the upcoming forecast has, we can match the observations that occurred at the same time as those similar hindcasts. So the methods that we use are we download CFSV2 snow water equivalent forecasts and National Snow and Ice Data Center observation data sets from October 2012 to September 2021. Lead times for 1 to 4 months were selected from each forecast and concatenated into 4 separate continuous time series. June, July, and August were removed because there's not much snow in the summertime. A separate peer analog model was trained on each lead time for 1 to 4 months and trained on the 2011 through 2019 water years, and then was tested on 2020 to 2021. Multiple analog numbers N were tested, but we found N equal 3 showing the best results while minimizing computational costs. So when N equals 3, we go back and find the 3 most similar hindcasts and average the observations that occurred at the same time together in order to create our future forecast. So the N most similar analogs were found by minimizing a cost difference function between test forecast days and training reforecast days with the same lead time. Then the average NSIDC observations respective to each analog day. The daily forecasts were averaged together to make a monthly forecast, and the long-term averages, biases, and area average time series were compared for analysis. And this is what the final forecasts look like. The 1, 2, and 3 month lead times all look the same because they're for the same time frame, so this is actually a good thing. The top shows the observations, the middle shows the bias in CFSV2, all the blue is mist snowpack in the mountains, and the bottom shows GARD. There's much less bias overall. We look at the correlation for the overall area average of the plot that you can see on the left, and we find that the GARD, analog regression downscaling that we've made, has a much higher correlation than the original CFSV2 forecast. And one interesting thing that we can see is the correlation for CFSV2 starts out around 0.4, it drops to 0.3, and then jumps back up to 0.5. This means that the CFSV2 actually has more accurate snow water equivalent at longer lead times than it does initially. This is because the initial conditions are so bad that the snowpack that it builds is better than what it's initially seeded with. And this is slightly reflected in GARD, although the correlation in GARD is improved at all lead times. We then look at the average bias. The blue is from CFSV2, the red is our downscaled model GARD, and the green is climatology. Climatology is simply averaging the last 30 years of snowpack together, and it's what the government currently uses. But when you plan for the average, as you can see, we never actually get the average. And so GARD generally has less bias than both CFSV2 and the climatology. And lastly, we look at the bias by elevation bins. And so what we can see is the SWE gets higher and higher at higher elevation ranges. And then in CFSV2, that bias becomes larger and larger as the elevations increase because it's not forecasting any of the mountain snow. The bias in GARD, however, tends to be a lot more consistent. It averages out to a bias near 0 and has roughly equal over and underestimates at the higher elevation areas. And I'm proud to say that GARD is now a live model on the Utah Climate Center website, which is updating 4-month snow water equivalent forecasts every day as new snow CFSV2 data is released. So in conclusion, SWE is the primary water source for the Colorado River Basin. CFSV2 has low resolution and tends to underestimate SWE. This underestimation changes the energy balances in the model, leading to early snowmelt, warmer temperatures, and other model variables. And analog downscaling shows mountain snowpack at higher resolution, improves the correlation, and has less bias. So now that we have a downscaled snow water equivalent forecast, there were a lot of hoops to jump through to get there. It would be much more simple if we could just downscale precipitation and temperature separately, and then just use that to help us inform a future model. So in order to do that, we have to know when it rains or when it snows. And so this is improved rain snow partitioning in the Northern Hemisphere with decision trees. And so the picture on the left is from hiking up the canyon one day. It had recently snowed or rained or both. And so the whole top of the canyon had snow and the whole bottom had rain. So this entire chapter is essentially trying to predict what areas it will snow and where it will rain. So then we can predict roughly where these snow lines occur. So how do we separate rain from snow? What we think happens, and is most logical when we're taught as young kids, is that when the air temperature is above freezing, it rains, and when it's below freezing, it snows. However, it's a lot more complicated. In reality, it's a curve. And so this curve indicates that it can both rain and snow across a shared temperature range. In addition, that curve changes in location between different places. What we later find is that the main driver is relative humidity, but there's a lot of factors going on that create a different curve for different locations. So the goal of this chapter is trying to figure out where we land along the curve and whether rain or snow is most likely to occur there, and trying to understand a little bit about what makes these curves fall in different places for different locations. The way we gather the snow and rain data is through observations. You see, weather stations are not widely equipped with technology which can actually tell us whether it rains or snows yet, and so we rely on human observers. When the weather station assumes it rains and it's above freezing, a human reports via their phone that it was actually snow. And we can combine millions of these observations together for further analysis. We use the NSEP ADP operational global surface observations, which has more than 71 million rain and snow observations from February 1975 through February 2007. The distribution of all those precipitation areas are shown on the right. And you can see that, interestingly, the peak in the precipitation events is actually near freezing, showing that we really need to be able to understand when it rains or snows near freezing. To simplify the data set a little more, we only focus on the range from -8 to +8 degrees Celsius. This is the area in which it can either rain or snow. And there are 3 different ways which we can measure temperatures. They are all measured at the 2-meter height above the ground. The first is air temperature. It's just simply how hot or cold the air is. This is the most simple and logical and easily accessible type of temperature data. The second is wet bulb temperature, and this is how cool the air is when water evaporation occurs under constant pressure. As water evaporates, it takes some energy to evaporate the water, which cools the surface a little bit. This is why we sweat. And so we are basically modeling each hydrometeor as a tiny sweating droplet. And the last type of temperature is called dew point. This is how cold the air must be to become fully saturated with water and condense. When it fully condenses, clouds and fog form. And so under this, we are basically modeling the hydrometeor as a tiny falling cloud. And when we compare dew point, wet bulb, and air temperature, because of how they're calculated, the dew point is always less than or equal to wet bulb, which is less than or equal to the air temperature. And all 3 of these are equal when relative humidity equals 100%. We use the decision tree method in order to help sort out the most important variables. We use 10-fold cross-validation across these 16 million data points between -8 and +8 degrees Celsius. The inputs are longitude, latitude, elevation, hour of day, the air temperature, dew point, wet bulb temperature, relative humidity, and air pressure. This is all the data that we could get from the data set that could possibly inform us when it may rain or snow. And the output is a simple snow phase. It's either true, it snowed, or false, it rained. And the initial decision trees that we make by default are really big. They have over 60 different decisions. And admittedly, we don't need all those. It overcomplicates things. And it also leads to overtraining, in which we become too specific at fitting our training data set and end up losing a little bit of accuracy on the test data set. And so what we do is we prune the tree. We use cost complexity pruning, in which we use this little alpha term in order to compare the size of the tree with its accuracy. And when we do that, we end up slowly stripping away nodes and making the tree less and less deep until we end up having just a depth of 1 with realistically a single if-then statement. And what we find is the accuracy doesn't really change as we prune the tree. So we end up going with the most simplest answer. And that is that wet bulb temperature less than or equal to 0.456 degrees Celsius ends up giving us a 93% accuracy. Because we're curious, like, are all these other variables just useless? We end up taking wet bulb temperature out of the data set and retrain the tree. And we end up with a very similar example. However, it's based on air temperature being less than or equal to 1.15 degrees Celsius with a 92% accuracy. And lastly, followed by dew point with a 91% accuracy. We compare the accuracy of these three trees, thinking maybe one might do better than the others in specific scenarios. But when we look at the entire air temperature, wet bulb temperature, and dew point ranges, we find that wet bulb is still the most accurate model, especially in scenarios where we have relatively low levels of relative humidity. And then we get curious and find that the wet bulb decision thresholds, if you train on each individual station across the Northern Hemisphere, we find that even those still vary quite a bit. And we tried to look into it a little bit. We couldn't find any patterns. I attended a conference and found someone else that did a whole study trying to find patterns on what changes the wet bulb decision threshold spatially, and they couldn't find anything either. So this tells us that there's things that we don't know how to measure yet that end up telling us whether it rains or snows. And to further cap off this study, we teamed up with a statistics student, and through entire advanced machine learning models that take thousands and even millions times more complicated than the single if-then statement that we found, and they couldn't even get above the 93% accuracy. And included in this were both temporal trends and even vertical temperature profiles, and they still couldn't get past 93%. So in summary, rain and snow can both occur between -8 and +8 degrees Celsius. The tree is pruned down to a depth of 1 with no significant losses in accuracy. Then wet bulb is the single most accurate variable, followed by air temperature and then dew point. And even advanced machine learning methods are not significantly more accurate than using this simple wet bulb decision. So now that we know when, or as best we can, we end up understanding when it rains versus when it snows, we look towards models which use these same rain-snow partitioning methods based off of wet bulb. And we want to understand how this changes the effects in snow fraction trends. So how much it rains versus how much it snows over a given year. And so from this, we move on to the effects of temperature and humidity on global snow fraction in ERA5 reanalysis and CMIP6 models. So this goes back to the 2023 record winter precipitation and snow year. And on the left, we have the total amount of winter precipitation. On the right, we have the total snow water equivalent. It's not surprising that we received a whole lot of winter precipitation and we got a whole lot of snow out of it. However, when we look at this year, it shows that we had actually pretty close to average winter precipitation, but we received much lower snow water equivalent levels. And this is because, for anyone that's lived here, you had to shovel your driveways a whole lot less this year than you did in 2023. And that's because much of the precipitation that fell, especially in the low elevation valley regions, was rain instead of snow. And this does two things. One, when it rains, rain is not snow, so it can't contribute to the snowpack. But it's even worse than that. When rain falls on top of snow, it tends to actually melt it. And the loss in snow water equivalent from the rain can actually be greater than the increase from the rain to other regions. So, in short, when it rains on snow, that's worse than it just not raining at all, a lot of times. And it's important to keep this in context that when we look at these temperature trends across the world, they are often strongly based on temperature. And as we know, with the global warming and climate change, the temperatures are slowly drifting to become warmer. But on top of that, their distribution also changes. As you can see, it's slowly getting shorter and wider. And this means that not only is the temperature warming in its trend, but it's also having more and more days that are warmer than average or colder than average with climate change. This amount that it changes is called climate variability. So the model that we use, because it's based off of wet bulb temperature, is the ERA5 reanalysis model. This stands for the European Center for Medium Range Forecasting Reanalysis 5th Generation. It's a reanalysis data set. And so when we looked previously, we were looking at individual weather stations. However, we can't put a weather station everywhere across the whole world Otherwise, it would be extremely inconvenient. So what we do instead is we take the weather station observations and we put them into a climate model. This keeps the climate model from tending to drift, and we call it reanalysis because we're reanalyzing the data set. And so we use the actual station observation data, but then we fill in the gaps, so to speak, between the stations with model dynamics. And this gives us the most accurate representation of a continuous map that we can have. It has a 0.25 degree resolution, which is high enough to actually pick up the large mountain ranges, which was important for the study. And the variables that we downloaded were 2-meter temperature, humidity, total precipitation, and snowfall. On top of this, because we're using only the ERA 5 reanalysis data, and we want to be able to compare it with other models, we download CMIP 6 historical models. This is the Coupled Model Intercomparison Project Phase 6, and it's an international standard of comparison. So if anyone tries to create a new climate model, they have to compare it with these in order to prove that it's accurate. And these are historical models. So they're not what actually happened exactly, but instead what they are is we began running them back in 1950, and we let them run with their model dynamics. The range of temperatures and amount of precipitation and all of these variables are realistic for what could have occurred over the last several years. And it gives us a range of possibility for what the Earth could have done. They have a resolution that's much lower, between usually 0.5 degree and 1 degree resolution. And from this, we download the 2-meter air temperature, total precipitation, and snowfall. And so when we look at the ERA 5 trends in temperature and snow fraction, it's not surprising to see the 2-meter temperature warming, as we can see in the red line, and the snow fraction, which is the percent of total precipitation falling as snow, is slowly decreasing. And we calculate a correlation between these two of being negative 0.8, but there's a catch. Because both of these trends are in opposite directions, it could be that they're just connected because of their trends. Instead, we sort out the variability by detrending the data set. What we do is we subtract those bold trend lines, and it makes the entire data set flat. And then this allows us to compare the warmer than average years with the years which have more or less snow fraction than normal. And as you can see, it tends to follow these inverse curves. And we find that the correlation is still pretty strong at negative 0.656. So this means that around 0.15 of that negative 0.8 correlation in the first plot is from the trends, and the rest of it is from the variability occurring at roughly the same time. We also do this with relative humidity. However, there's not nearly as strong a trend in relative humidity. It has initially a very weak correlation. And when we detrend it, it literally has 0 correlation. So relative humidity on a global scale does not significantly affect snow fractions. And we want to compare this correlation in ERA 5 with the rest of the CMIP 6 historical models. And when we do this, we find that the CMIP 6 historical models all have a very similar detrended correlation in the negative 0.6 to negative 0.8 range when we detrend the correlation. In addition, we notice something else about the CMIP 6 historical models. They have a very strong cross correlation between the 2-meter temperature trend and the snow fraction trend. So the line plot shows on the x-axis the 2-meter temperature trend in how quickly things are warming, and the y shows the snow fraction trend in how quickly the snow fraction is decreasing. And what we find is that they fit along a nearly perfect line. And this means that the models which have higher warming rates will also show faster decreasing losses in snow fraction. And this becomes extremely important when we can assume that if this is true here, it is probably also true in future projections, which have different emissions levels, which then give them different warming rates. So in worlds in which we continue to warm at faster and faster rates, we will also have faster and faster losses in snow fraction. And then lastly, we look at the spatial correlation between the detrended 2-meter temperature and snow fraction. On the top, you can see the average temperatures in ERA 5, and on the bottom is these detrended correlations. And what we find is that there's this freezing line one in the northern hemisphere and one in the southern hemisphere, as you can see in the white, where the average temperature year-round is close to freezing. And in the bottom, you can see these very strong inverse correlations in red, which roughly follow these freezing lines. And so what this tells us is that areas with average temperatures near freezing are the most at risk for changes in snow fractions under future climate change. And because of this, when we think back to the snow fraction curves with air temperature, that snow fraction curve begins to drop the fastest right around freezing, which makes complete sense here. So in summary, the ERA5 and CMIP6 both have an increasing temperature trend and decreasing snow fraction trend. The temperature and snow fraction have a significant inverse correlation in both ERA5 and CMIP6 historical models. The CMIP6 historical models with high warming rates also have faster snow fraction loss. And temperature has a major inverse correlation in spatial maps where average temperatures are near freezing. We also looked at relative humidity spatial maps on that they have a much more minor role to temperature. And so, because these are models and they are based off of wet bulb temperature, they're certainly the most accurate that we can get. However, it would be really cool if we could actually measure the physical snow fractions at a given weather station. And so this leads into my last chapter, which is all about measuring precipitation phase remotely with dual heated precipitation detectors, which I have right here. And this is the work I've been doing in collaboration during my internship with Apogee. So Apogee Instruments created the heated precipitation detector. Its goal is to detect when precipitation falls. And so it's relatively small and a lot lower cost than most other precipitation sensors. And this makes them a good candidate to be able to deploy at lots of weather stations around the world. And they work based off of permittivity. They're a capacitance sensor. And when we look at permittivity, this is how much effort it takes to polarize a material and how much resistance it has to being polarized in an electric field. So conveniently for us, air has a relative permittivity of almost exactly 1. And water has an extremely high relative permittivity of about 80. So when you put water on one of these devices, the signal is much higher than it has in dry air. And so we end up, and we can hypothesize that what if we use the heater in one to melt snow and we leave the unmelted snow on the other device? What we would then have is water on one device and a combination of air and water on the other. And we hypothesize that you can get something similar to this graph that I've sketched out. In red shows the heated signal, which is extremely high, and the one on the unheated device with snow would have a more medium signal in the middle. In order to make these sensors as accurate as possible, we include a temperature correction into them. And this corrects for both day-to-day variations in temperature from the day to the night. And it also corrects for seasonal changes from winter to summer. And lastly, it also corrects for changes in temperature from the internal heater itself, so that the signal has the least amount of change possible across all temperature. And also, because so many snow and small precipitation events can be extremely light, they can get blown around the wind, and we risk not being able to detect them at all. So we include wind rings on them when we put them out in the field, as you can see on the left. And the bottom right shows an example in which there is no wind ring on the right, and a wind ring is included on the left. And you can see that we actually pick up these light rain events and snow events in the orange heated HPD data when we have the wind ring installed. And so in practice, our theory actually works out to be pretty good. Whenever precipitation falls on the device, it quickly evaporates the residue. So the heater also increases the evaporation rate. And in that first example on the left, both the signals are similar, indicating that it was the result of rain. Then, interestingly, the heater actually prevented frost from forming on the device. So it helps us differentiate between actual precipitation versus dew and frost. And then when it snowed a few days later, we did in fact have significantly different signals, indicating that, yeah, the dual HPDs can actually work. And a few days after that, we had a really light snow event, which had just a few snow flurries, and we were still able to pick that up, melting the tiny snowflakes and having a much lower signal on the unheated HPD. We can also collect the temperature data from the HPDs, and you can see that the temperature increases when the heated HPD gets wet. And then it also is programmed to maintain a temperature just above freezing whenever it's dry. And this allows us to begin melting snow immediately once it starts falling. And lastly, we assign a wet-dry flag. This is simply the signal at which we decide when the sensor is actually wet. We used about a year's worth of field data in order to make this decision, along with putting water on it in different amounts with tiny little water droplets. And we decided that a signal being larger than 1500 indicated that it was wet, and a signal being less than 1500 indicated that it was dry. If we fully saturated it with water, dumping a whole bunch of water on it, the highest signal we could possibly get was a little bit over 20,000 for comparison. So these sensors are extremely sensitive. And then lastly, we have actual field data. We were able to deploy a set of HPDs on the rooftop at Apogee and also one out in the field up Logan Canyon in the high mountains that receive a lot more snow. So this is from the field data up the canyon, and we can see the two pairs of HPDs and their signals in the top two rows. The heated HPD had a much higher signal than the unheated HPD, but they were both considered wet, and so this leads us to have a very clear conclusion that it was probably snow. The middle shows the ratio of the two, which we're trying to experiment with to try and define the difference between the two signals. The fourth row there is SNOWTEL station data with the snow depth in blue very clearly increasing when the HPD signals also increase. This tells us that it was actually an increase in snowfall and not just rain. And lastly, the temperature from the SNOWTEL site in black and the unheated HPDs in red and blue are all significantly below freezing, further confirming that it's most likely snow. Then we ran into some problems sometimes. One of them was that if snow fell one day and then didn't fully evaporate, that it would leave residue. And so when this happens, the unheated signal is still significantly higher than it would otherwise be. And this means that our whole ratio that we were using before tends to fail in these scenarios. And so snow with residue definitely makes things a little bit harder. And the last problem that we ran into was the mixed phase. So this shows that when it initially started having precipitation forming, it was a little bit close to or above freezing. And the signals are very similar. This leads us to believe that it was initially rain. But then later on, the signals differentiate, and they're actually different again. So that tells us it was snow. So at some point during this precipitation event, it started as rain and then transitioned to snow. When exactly? We can't tell because the rain and the snow mix on the device. And so we need a lot more test data from the field in order to better understand these mixed scenarios when it actively transitions between precipitation phases. And so the end goal is to try and automate this. Instead of just looking through and saying the signals are different, it must be snow, we want to be able to automatically assign a category to the end user so they can then understand what actually happened at their weather station. So we create different categories. The first being dry. If both signals are less than 1500, then that's pretty easy. It's dry out. The next category is residual, in which the heated signal is less than 1500 because the heater evaporated all the water off of it, but the unheated signal is greater than 1500. We then have rain, in which both signals indicate that the sensors are wet, and they are roughly equal because they both have liquid water on them. And then we have snow, in which both sensors are wet, however, the heated signal is significantly higher than the unheated signal. And as you saw, the residual needs to be removed before the next precipitation event. We certainly have ways that we can experiment with trying to help with this. And then the mixed phase, where it's either falling in between, not exactly snow or rain, or it transitions between the two. We just need a lot more data to understand exactly when this is happening and what the sensors react. So in conclusion, with some improvements, the dual HPDs have excellent potential to be able to detect precipitation phase and timing in remote regions. So the overall conclusions of this entire research is that forecast weather regimes made with Gaussian mixture models can be linked to historical precipitation patterns to improve CFSV2 precipitation forecasts. 2, the analog downscaling with GARD can be used to increase CFSV2 SWE forecast resolution and accuracy in the Colorado River Basin. The third, a single depth decision tree based off of wet bulb temperature is currently the most accurate and efficient method for rain snow partitioning. Fourth, warming temperatures are decreasing snow fractions around the world, especially in areas with average temperatures near freezing. And lastly, dual heated precipitation detectors have great potential for physical measurements of precipitation phase and timing. And if there's certainly one thing I've learned while doing a PhD or anything difficult, it's that whenever you do something this big, there's going to be a whole lot of ups and downs. The progress won't always be linear. And even when you think you reach the end, there's always going to be another mountain to climb. I'm fortunate to be able to have 3 first author manuscripts already from my work with Dr. Zhang, as well as 4 other co-authored manuscripts that helped me learn along the way. And I would like to say a big thank you to my family, as well as my committee members that are all in attendance today. In addition to some collaborators, both within and outside of the department, that I was able to help publish manuscripts and give feedback on the studies that I've done. The staff from the local department, Lori and Desiree, and as well as all the people at Apogee. Most importantly, Dr. Bruce Bugby, the founder, Mark Blomquist, the head scientist, and Ryan Lindsay, the head engineer. I couldn't have done it without you guys. And so with that, I would love to welcome any questions. We will have a post-defense party from 5 p.m. to 8 p.m. at Bridger Park. So yes, please have any questions right now, and then we will move forward with talking with the rest of my committee. Thanks.
Cody, where does thunder snow fit in?
Where does thunder snow fit in? We had thunder snow. So lightning occurs whenever there's static electricity between the hydrometeors in the cloud. And so thunder snow would just tell us that there's a lot more energy between the snowflakes and or maybe raindrops up in the clouds, which allows lightning to occur. But obviously there's a lot less water in snow than there is in rain. And so it's more rare, but it certainly does happen. Yeah.
Towards the beginning, you had a
national
water usage map
in
the United States. And it could just be me as a bad listener. I was curious if that had to do with percentage of like rain and like fresh water that's available to how much people are using, or if it's just how much people are using and those higher usage states happen to be drought ones.
It is just simply how much people are using. However, you tend to need to use less when you have more. Like a big part of why Utah ends up using more water is because watering our yards, because if they don't get as much rain, then you have to water them more often, and things like that. So the answer is, it is purely water usage. However, they are connected, and there's a reason for that. Yep. Yes. Yes, Bruce?
Your early reps had that nice curve with rain and snow, and it was how you phrased it nicely. When you were a kid, you just say it's below freezing and snow, it's above freezing and rain.
Yes.
Yeah. Now your next question. My understanding is that data comes from human workers. They're looking at something and say, right now it's snow and Right now it's raining.
Yes.
Is that right?
Yep. Yes, just like this.
Are in places where people live, right? They're not camping out at the top of some mountain all winter.
Yes.
Checking rain and snow.
Yes, the human observers sleep often at night. And so we will miss a whole lot of precipitation observations from that. And as on top of that, as you're explaining, one of the goals of the HPDs is to be able to deploy them at remote sites where we can actually get more of this mountain snow fractions where understanding snow is the most important.
And even if they were everywhere, there's that mixed precipitation where a human can barely tell.
Yes.
Is this water?
Yes. Yes, the mixed precipitation is not consistently defined across countries or across science groups. And so even those areas where we end up defining mixed in the HPDs is just as, if not more, subjective in reporting mixed from human observers. I watched an entire presentation about it from a guy that I've collaborated with named Keith Jennings. He maxed out at that 93% that we had talked about, and he organized the whole data set that I used. And so his whole presentation this year at AGU was what is mixed precipitation? And I feel like he made us all even more confused than when we started.
Snowpack is so important, and we don't record snowpack in non-clear at all. That's why it has to be hard coverage.
Yes, Kat? Whether it snows or rains. So, yes. We talked about this. It will impact the density of snow. However, I don't think that wind itself has a significant effect on whether it's rain or snow as a phase. That makes sense.
So if these sensors are put higher up in the mountain, is that the solution for being able to get a better than 93% accuracy?
It's not the solution, but it will give us more data points in these extreme areas. And so from having more data points, we can then look at the data to try and find more in-depth patterns. Yeah, and so it can certainly help. And if nothing else, it can help us understand the actual trends in snow fractions over the year. Because we don't actually know exactly how much it rained or snowed in the mountains this last winter. We had record low snowpacks, but that's a big part because it just rained so much in the valley. But every time we looked up there, it was snow. And some of the mountains could have had close to average snowpack, but it was just all canceled out by the state averages. And we're probably never going to know for sure. Yes? Yes, it was here. We did try random forest. It was actually worse than the decision tree, which. Yep. Yes, it's the NCEP ADP Operational Global Surface Observations. If you're interested, I can share with you the manuscript by Keith Jennings, in which he created. Well, this is a global observation data set from government observations that are all globally reported. And yes, yep, someone's there and they write down whether it rains or snows. There will be a little bit of bias. Yeah, these are from more official government workers rather than citizen volunteers, as other studies have used. But yes. Yep. I know, we thought actually, yeah, we had all of these variables included in the decision tree. The first tree that it printed out was so big I couldn't read it. So then we started pruning it. But as we pruned out more and more variables. On the far right-hand side, that's just a single depth of 1 with no significant loss in accuracy. So we did initially include those variables, and the decision tree said that these don't in terms of accuracy. Correct. Yes, that was one of them. Yes. Yeah. But I mean, the wet bulb temperature will change with elevation. So that's indicative of it. Yes, because higher elevations have lower humidity, which lower wet bulb temperatures. Yes. Yes, John?
93% is pretty good. Showed the difference in the evolution of accuracy, at least in the dissertation. And it seemed like the first methods that we've been doing based on simple temperature criteria for 30 years was 91%, 2%.
Yeah.
So we have all these new methods that have brought us an extra 1%.
Yes. Within the -8 to +8 degrees Celsius range.
You've got a lot of data points, a ton of data points to look at. I'm curious if you could talk about what that last 7% of apparently unsolvable precipitation types, what's happening now? Are those all clustered at a temperature range? Are they all over from -8 to +8? What's that last 7% that we can't get even with Elon Musk's supercomputer algorithms? What's missing for that 7%?
That's one of the things that we really don't understand yet. This plot was because it shows the accuracy over each variable. And all that we really found was that near the decision point is where each variable is the least accurate. And then in addition, at really low relative humidity levels. And so we don't actually really know where that 7% is from. That was one of the main goals of this study. If we could have picked up like 1 or 2%, that would have been great. What we assumed was the case was that we needed to incorporate the vertical temperature profiles, which is what this plot was showing, because it matters both the temperature where it forms as it falls and at the surface. And so, but yet she included the vertical temperature profiles from ERA5 and found that she couldn't increase the accuracy. And so that's because of one of two things: either the ability for ERA5 to simulate these exact temperature profiles vertically over smaller scales isn't accurate enough, or vertical temperature profiles don't have as much as we thought to do with them. And we will need a higher resolution vertical profile data set paired with all these rain and snow observations in order to be able to tell for sure.
The geographic hotspots where the problem becomes more of an issue. I'm curious because humidity is maybe the most uncertain variable in reanalysis.
Yes.
And you have very, very precise your wet bulb to the degree. Humidity is a huge challenge just to measure with sensors and then to extrapolate that over complex terrain and then subject it to very precise thresholds.
Yes.
Is that a potential source for the bias? That 7% is coming from areas where the humidity is just poor in terms of how we're characterizing it?
Yes, that is certainly another possibility, because the relative humidity in this case was taken from another reanalysis data set. And so that by default has imperfect dynamics and lower resolution. And so those differences in both relative humidity and vertical temperature profiles together could contribute to that last 7%. Yeah. And if we had them at a weather station, we'd know exactly what it was.
One question for Cody?
Yes.
The residual issue of a statistics there at the
Yes. One of them, Rustin, who's actually here, is actually working on a tiny little wiper for another sensor. So we could install basically a tiny windshield wiper. If that doesn't work, we also had the idea that we could just dump the whole HPD upside down every few minutes and that would effectively dump off all the precipitation and let new precipitation accumulate. Yes, this last year was the first year that we had the finalized HPD product, in which we didn't actually change any of the settings for the entire snow year, and we learned this from it. And so if this project is continued over the next couple of years, that's certainly the next challenge that we plan to try and overcome. Yeah. Yes. Yes. Which one? The precipitation or the snowpack? Okay. If it's worse, in which places? Oh, yes. CFSV2 is over predicting precipitation. Is that what you're asking? Yes, let's see. I need to check the overall bias. I didn't include the overall bias in this, but I did include it in my writing. And so I'd have to check that because this is just one example that I use to explain what an example forecast looks like. And so some of the other times may have had a positive bias over, or a negative bias over larger regions. So I need to check before confirming that CFSV2 does consistently have a significantly high bias.
All right. Let's give a this will be followed by some questions from the committee. They have a lot of questions. Yeah,
Thank you. Thanks. Thank you. You can take it.